Today, well, we're diving into something truly fascinating. This age-old dream of turning lead into gold.
It's such a classic idea. This Chrysopia, is that how you say it?
Recipe, yeah. Gold making. It drove alchemists for centuries. And what's amazing is how this magical quest connects to really cutting edge science today.
Totally. We've got some great sources lined up. We'll look back at the history, what alchemy was really about, what they believed.
And then we jump right into the present day to CERN
Yeah.
and the Large Hadron Collider, some mind-bending experiments happening there.
Exactly. So the mission today is to connect those dots, the ancient dream, the modern science, and figure out what it all really means, for you without getting totally lost in the jargon. Okay, let's get into it.
All right, so Chrysopia, it's ancient Greek, literally gold making, like you said. And it wasn't just a side project, it was central to alchemy, right alongside making silver, argyropia.
Wow. And this goes way back.
Oh, yeah. Figures like Zosimus of Panopolis, around 300 AD. And it kept intriguing people, even much later. Think Robert Boyle, 17th century, big names.
It's wild to think about their worldview, though.
Uh-huh.
Trying to do this based on, the four elements? Earth, air, fire, water.
Uh-huh. And that metals were essentially made of mercury and sulfur. It seems basic to us now, but that was their model of reality.
A completely different framework.
Exactly. Their theories, okay, they're obsolete now, but they came from a real desire to understand what stuff is made of, just through a different lens.
And then there's the Philosopher's Stone.
Mm-hmm.
The ultimate MacGuffin, right? Supposed to transmute metals and give you immortality.
That was the dream, a powerful symbol, really, of wanting wealth and, well, not dying. Pretty universal desires.
And the actual lab work they did, refining, distilling, alloying, that sounds like early chemistry, doesn't it? Or metallurgy.
Absolutely. Even if the theory was off, the practical work was important. They were learning about materials, how things reacted.
Laying groundwork, even if they didn't know it.
For sure. Alchemists were often meticulous, kept detailed notes. They're usually in secret code,
Right, the secrecy. Made it hard to share knowledge, I bet.
It did, but it shows they were serious. And, there were always claims, stories of success, which just kept the dream alive, even without solid proof.
And it wasn't just lone eccentrics. You had clergy, nobles involved.
Oh, yes. Though the church sometimes condemned it, saw it as maybe stepping on God's toes, adds a whole social layer to it.
Fascinating. And you mentioned an anecdote.
Ah, yeah. Johann Friedrich Butger, early 1700s, the king of Saxony basically locked him up and said, "Make me gold."
High pressure. Did it work?
Nope, failed completely at making gold. But in the process, he accidentally figured out how to make European porcelain, which was huge.
No way. So he found white gold instead of yellow gold. Sort of.
Kind of. A pretty amazing accident, right?
Definitely an unexpected win. Okay, so let's jump forward. Centuries later, we leave alchemy behind and get into, proper 20th century physics. This is where changing elements gets real.
This is where it gets real scientifically. Understanding radioactive decay, how some elements just naturally change, and then figuring out how to make them change, like bombarding them with neutrons. That was the breakthrough.
Right. And Glenn Seaborg plays a big role here.
Huge. His synthesis of plutonium in 1941 was massive. Proof humans could actually create new elements using nuclear reactions.
Wow. And then didn't he actually manage the lead to gold thing later?
He did, in 1980. Deliberately turned a tiny, tiny amount of lead into gold. A huge symbolic moment, bridging that old alchemical dream with actual science.
Incredible. And wasn't there an accidental case, too?
Yes, good point. Back in 1972, apparently, at a nuclear reactor in Siberia, some lead shielding unintentionally got zapped into radioactive gold.
Whoops.
Yeah. So these events showed scientifically transmutation was possible, but doing it efficiently or on a large scale, that was still a massive challenge.
Okay, which leads us right up to the present day. CERN. The Large Hadron Collider. This is where the science fiction starts to feel a bit more like science fact, right? Even if it's still on a tiny scale.
Exactly. The Alice experiment there. They've managed it by smashing lead nuclei together at incredible speeds, ultra-relativistic speeds.
Meaning almost the speed of light.
Pretty much. The energies are immense, and when these lead nuclei collide or even just miss each other very closely, they create these super intense electromagnetic fields, like incredibly powerful flashes of light.
So it's not always a direct hit. These near misses, ultra-peripheral collisions, you called them.
That's the key for the specific process. In those near misses, the electromagnetic fields basically act like high-energy photons, light particles.
Oh, yeah.
And this light, this photonuclear interaction, it can actually knock protons and neutrons out of the lead nucleus. It's called electromagnetic dissociation. They use lead-208, which is a stable type.
And knocking particles out changes the element, so you just need to knock out the right number.
Precisely. Lead has 82 protons. Gold, the stable kind, gold-197 has 79. So if you can manage to kick out exactly 3 protons from that lead nucleus, you get a gold-197 nucleus. And the detectors at ALICE, they've actually seen this happen.
Wow. And they have special gear just for this, these 0-degree calorimeters.
Designed by Italian researchers specifically to catch the particles flying out along the beam pipe after these near-miss collisions. It's incredibly precise stuff.
So how much gold are we talking about? Do they make a lot?
Well, a lot is relative here. During LHC Run 2, that was 2015 to 2018, they estimate about 86 billion gold nuclei were produced across all the main experiments.
86 billion. That sounds huge.
It does, doesn't it? And the rate is about 89,000 nuclei per second when it's happening.
Per second. Okay, so time to buy a bigger vault.
Hold on. Because the total mass of that gold over 3 years was about 29 picograms.
Picograms. Okay, translate that for me. How small is a picogram?
It's a 1 trillionth of a gram. So 29 picograms is vanishingly small. Think less than a trillionth of the weight of a tiny grain of sand.
Right. Okay, so 89,000 atoms per second sounds fast, but the atoms themselves are just incredibly light.
Exactly. Scientifically interesting, yes. Economically significant. Not even close.
And I assume this gold doesn't exactly stick around for long either.
You assume correctly. These gold nuclei are created unstable with loads of energy. They last for about a microsecond, a millionth of a second.
A millionth of a second, so you can't even collect it.
Nope. They basically instantly hit something else in the accelerator or just fall apart back into protons and neutrons. Collecting it is completely impractical.
So the alchemist's dream technically achieved, but maybe not quite in the way they imagined. No bars of gold coming out of CERN.
Definitely not. Which brings us squarely to the economics and practicality, doesn't it?
Yeah. Running the LHC must cost a fortune in electricity alone.
Oh, it's immense. Around 700 gigawatt hours a year. That's like powering a decent-sized city or hundreds of thousands of homes.
Wow. And compare that energy cost to just, mining gold the old-fashioned way.
There's no comparison. The cost of mining, the all-in sustaining cost, was around, what, $50, $1,400 an ounce in 2023?
Something like that, yeah.
The energy cost alone to make even a tiny bit of gold at the LHC would be astronomically higher. Many, many orders of magnitude more expensive. It's just fundamentally not an energy-efficient process for bulk production.
And even with bigger, better colliders in the future, they won't suddenly start churning out tons of gold?
Not a chance. The total global gold mining output is over 3,000 tons a year. Even with upgrades, the LHC or future machines might produce slightly more than 29 picograms, but it would still be an utterly negligible amount compared to mining.
So particle accelerators just aren't designed for this kind of mass production. It's about precision, not quantity.
Exactly. Only a tiny fraction of collisions result in gold. You need incredible precision to make it happen and even more to detect it. Marco van Leeuwen from ALICE talked about how sensitive the detectors have to be. It's a delicate balance.
And then there's the cost of building the things in the first place. Billions.
Right. So you spend billions on the machine, use a city's worth of power, and you produce, well, that 29 picograms. Its market value is about $0.00000015, roughly.
Okay. So safe to say the gold market is safe? My fillings aren't going to suddenly become worthless?
Not from CERN, no. Gold's value comes from its rarity, its uses, and this stuff barely exists. And only for a microsecond. It has zero market impact.
Which really brings us to the why. If it's not about making gold, what's the point of these experiments? What are the real takeaways?
That's the crucial question. The value isn't in the gold, it's in the physics. These experiments help us test and refine our fundamental theories about how matter interacts, specifically these electromagnetic interactions at high energies.
So understanding how the universe works at its most basic level.
Precisely. Understanding this process, electromagnetic dissociation, helps scientists tune the accelerators better, predict how beams will behave, and it tells us more about the structure inside the atomic nucleus itself.
Any applications beyond particle physics?
Potentially, yeah. Understanding these photonuclear reactions better could help astrophysicists model things like neutron star mergers, these incredibly violent cosmic events where heavy elements are thought to be forged.
Okay, so it feeds back into understanding where natural gold comes from in the first place. Cool.
In a way, yes. So while we've technically done what alchemists dreamed of, it really shows the difference between, scientific exploration and practical application.
It's curiosity-driven science.
Absolutely. Like John Jowett at CERN said, it's about fundamental physics. It honors that old alchemical spirit of inquiry, but grounds it in solid empirical science.
So gold is still going to come from mines, not machines.
For the foreseeable future, yes. The real gains from this research are in advancing physics and accelerator tech, not making cheap gold.
So quite a journey then, from mystical quests based on mercury and sulfur
And the Philosopher's Stone?
to these unbelievably complex machines using electromagnetic fields to chip away protons from lead atoms.
And the bottom line, yes, science can turn lead into gold. Confirmed.
But the amount is almost zero, it costs way too much energy, and it vanishes instantly. So utterly impractical for making actual gold.
That's the gist. The real gold is the knowledge we gain about the universe.
It really makes you think, though, that persistent human drive to figure things out, to chase these seemingly impossible goals.
It leads to unexpected places, doesn't it? Even if you don't reach the original, perhaps naive goal.
Yeah. What other alchemical dreams, things that seem impossible now, might science eventually figure out, at least in principle, even if they stay impractical? Something to chew on.